All right, our next unit is going to be on covalent bonding. Now, we just got done with looking at ionic and metallic bonding, and now we're going to investigate the last type of bonding that this class will focus on. That's covalent bonding. In a covalent bond, the valence electrons are shared. So what happens is if I have element X and it's got its electron cloud, its atomic orbitals, and it forms a covalent bond with Y, the electron orbitals of the two chemical compounds will begin to overlap each other. And in that overlap zone, that's where you're going to find the valence electrons, and that's where we're going to share the electrons. And these shared electrons then will count towards both the elements. Okay, so it's a way for both elements, in essence, to gain electrons. And this happens with nonmetals. Covalent compounds are found in compounds in which we have two or more nonmetals that bond with each other. Remember, in ionic bonding, we had a metal with a nonmetal, and the metal with low Coulombic attraction was willing to give or transfer its valence electrons to the nonmetal. When we have two nonmetals that come together and form a bond, neither one wants to lose. They both want to gain. So the only way they can both gain is by sharing electrons, creating these orbital overlaps where the electrons can be shared between each of the substances. Okay? The resulting compound that is formed is called a molecule. Okay, so when we have two or more atoms that are bonded covalently, form a shared relationship, that is called a molecule. Now, the type of bonds that can form can be a single bond, a double bond, or a triple bond. A single bond is where each element shares one electron each. And usually, what we'll see there is in a single bond, element X and Y will share a single bond. And a way we can denote that is by simply connecting the two valence electrons together, forming a single dashed line. That dashed line symbolizes a single bond, and it counts for 2 electrons total. And those 2 electrons are counted both for element X and for element Y. In a double bond, element X and Y will each donate 2 valence electrons. Each dashed line counts as 2, and this is a double bond. It almost looks like an equal sign. And a double bond is got a total of 4 electrons, in which 2 electrons are donated to each. And therefore now element X and Y each has 4 electrons accounted for with the double bond. And lastly, the greatest bond we can have is where element X, Y, and X and Y can each donate 3 electrons each, and that will then form a triple bond. In a triple bond, we have a total of 6 electrons, and again, those 6 electrons are counted for both element X and Y. One other type of bond I want to talk about is the style of bond. There's 2 basic types of covalent bonds. Now, single, double, and triple identify how many electrons are shared. But the type of bond that we can also talk about is nonpolar and polar. A nonpolar covalent bond is where the single or double or triple bond, where the electrons that are being shared totally equally. And this only happens when the 2 atoms have equal electronegativity. So if you can think back a couple units back to Unit 3, electronegativity is the affinity to pull electrons towards them in chemical bonds. Well, the only way you can have 2 elements that have the same electronegativity is if you have the same nonmetal bonded to itself. So they're very easy to identify. You just have to know that if you have carbon bonded to carbon or hydrogen bonded to hydrogen, it's the same nonmetal bonded to itself. It has equal electronegativities, and this is the only way that the electrons can be shared perfectly equally. Okay? And that is called a nonpolar bond. All other types of covalent bonds are polar bonds. So over 90% of all the bonds we're going to talk about are going to be polar bonds because they're going to involve 2 different nonmetals. And because they're 2 different elements, they have 2 different electronegativities, and therefore they each pull on the electrons in a not equal fashion, and therefore results is something called a polar bond, which we'll talk more about in greater depth later on in this unit. All right, so we're going to look at some different classic examples to look at different scenarios of each of these, so you have a good idea of how then to go ahead and do the homework problems, which is the next 3 pages. Okay, so in the workspace here we have the molecule hydrogen H2. So we have 2 hydrogens And the first thing you want to do is pull out your chem helper and identify how many valence electrons each has. Now, hydrogen has only got one valence electron, which is symbolized by a single dot. So again, that's the Lewis dot structure that we've talked about for the last couple of units. Hydrogen, the other hydrogen, also has one valence electron. And because they're nonmetals, they are going to share the electrons. And so all I have to do is connect the dots. And right there is the final Lewis structure for the molecule hydrogen. Okay, H dash H. And that dash is a single bond that counts as 2 electrons each. Okay, the type of bond it is, other than being a single bond, okay, is it a polar or nonpolar bond? This is an example of a nonpolar bond because it's bonded to itself. Now, I've talked a lot about in this class about the fact that valence electrons are shared or transferred to get up to 8 electrons. Well, hydrogen, you'll notice that each hydrogen atom has only got 2 electrons. Well, why is that? Well, hydrogen, if you remember, has electrons only on the first floor. And on the first floor, all we have is the 1s orbital. The 1s orbital is one single orbital, which to fill it, we only need 2 electrons. So each hydrogen atom has got 1 electron. So when they share, and both electrons are in the same orbital, we have 2 electrons that completely fill the first floor. So hydrogen is an example of an element down here in the very bottom, number 2, which is said to be a hypovalent molecule. Hypovalent means that it's a molecule that, or an atom, that is okay to have less than 8 valence electrons. And mainly because 2 electrons will completely fill the 1s floor, and therefore is a fully stable atom of hydrogen. So whenever we draw hydrogen, what you're going to notice is hydrogen can only form one bond, a single bond, and once it's bonded once, it'll no longer bond ever again because now it's its most stable configuration. All right, let's look at HF, the molecule HF. Again, H has got one single bond. F is a halogen. It has 7 valence electrons. And one thing you're going to get in the habit of doing with doing this is that with the only odd electron, you'll tend to face it towards the other element's single electron because that's going to be the bonding site. So then we'll connect the dots, and the final Lewis structure will look like that. Each of these double dots that's around fluorine do not count towards hydrogen. These double dots are called lone pairs of electrons. And lone pairs of electrons only count for the element that they surround. Okay, so right now the hydrogen, there's a dash that separates the H and the F. That dashed line counts as 2 electrons, and because they're sharing 2 electrons, they count towards each element. So this hydrogen right now has got 2 electrons around it, which makes hydrogen full because it fills the 1s floor. And the fluorine has got 2 electrons in the shared bond with hydrogen, the single bond, but it also has 3 lone pairs for a total of 6 more. So this fluorine now has 8 electrons around it, and it is satisfied by the octet rule. Fluorine has got its octet, or 8 electrons, by sharing with one of hydrogen's electrons. And now both elements are about as stable as they can be because they have filled their shells. Okay? The type of bond that it is, along with being a single bond, when it comes to is it polar or nonpolar, this is an example of a polar bond because it is between 2 different elements and they have different electronegativities. Now, what does that mean? Well, the molecule HF, F is much more electronegative than hydrogen. So in that zone where the electrons are being shared, fluorine has a much greater pull on that electron, and therefore it pulls the electrons into its electron cloud much more often. And since hydrogen's electron is pulled away from it due to it bonding with fluorine, the fluorine side of the molecule ends up developing a partial charge, which we signify by this little sigma negative. This stands for a partial negative charge, and the hydrogen's got a partial positive charge. In essence, the molecule HF has got 2 poles, a negative and a positive pole. So the molecule has got, in essence, with having positive and negative poles, it ends up being almost like a magnet. So then other HF molecules, when they combine, if they align in such a way that the positive pull of one molecule gets close to the negative pull of another molecule, there will be attraction. And that attraction causes cohesive forces, stickiness forces that causes the molecules to attract to one another. And that's called polarity, and that's something we're going to talk about in the end of this unit into further detail. So just for now, just understand a polar molecule just simply means that it has poles, a positive and negative pole, and that will lead to those molecules being able to attract to one another. Hydrogen, being nonpolar, does not really attract to itself and therefore has very low cohesive forces, and that also we'll learn what that does to its chemical properties. All right, the molecule water. This is the first time we see a molecule in which there are 3 or more atoms. When there are 3 or more atoms, there will be what's called a central atom. Can hydrogen be a central atom? Hopefully right now you're saying to yourself, no. Hydrogen, because it can only form one bond, it can only exist on the outside of molecules. It can never be on the inside and be what's called a central atom because it can only form one bond. So oxygen, immediately you should identify, will be the atom that's in the middle. And oxygen has got 6 valence electrons. It's in group 16 on your periodic table, something that you know how to do by now. The 2 dots, the lone pairs, tend to be sites in which bonds do not come off of. Only the single dots is where we'll typically form covalent bonds. So oxygen, we already predict will want to form 2 bonds. Well, water just so happens to be able to form those 2 bonds with 2 hydrogen atoms. So we put the 2 hydrogen atoms off of each of the single areas, connect the dots, and right there is the molecule water. Oxygen forms 2 single bonds with the 2 hydrogen atoms, and the oxygen has 2 lone pairs on it. And if we count the number of electrons around the oxygen right now, the 2 single bonds count for 4 electrons, and then we have 4 electrons in the lone pairs for a total of 8. Right now there are 8 electrons around the oxygen, and there are 2 electrons for each of the hydrogens because the single bonds count for 2 electrons for each element. So again, the hydrogen is full and the oxygen is full. It is stable as possibly can be. Again, these are polar bonds, and water is a polar molecule, and this is one reason why water will stick to itself so well. When water forms droplets, it tends to form very large droplets or will bead up on a surface, like on a rainy day, on your car hood, for example, and that's because water is very attracted to itself because it is a polar molecule. All right. Okay, oxygen, O2. There's only 2 atoms here of oxygen. So again, each oxygen atom has got 6 valence electrons. We will single bond the 2 electrons that face each other, and what you should notice right away is there are 2 single dots, one off of each oxygen. And usually whenever there is a single dot, that tells you that the molecule is incomplete yet. Now if I were to stop and count the number of electrons around each oxygen atom, there's a dashed line between the 2 oxygen atoms, so that counts for 2 electrons each. And there are 5 other electrons in each element. So each oxygen atom right now has got 7 valence electrons around it. Okay, 5 with the lone pairs and then the single dot along with the single bond. So oxygen is not at its octet. So what has to happen here is the only way it can gain more electrons is if these other single dots move in and now they form a multiple bond, specifically a double bond, and that's what happens. So in the future, when you start drawing Lewis structures, if after you single bond all the molecules, there ends up being extra additional single dots off of adjacent atoms, more than likely those single dots will move in and you're going to form a double or potentially even a triple bond. By it forming a double bond, each oxygen atom now is sharing 4 electrons total, and now adding the 2 lone pairs off of each, we end up having 8 electrons around each oxygen atom. Their octet is full, and now this is the molecule of oxygen. This is the molecule that we breathe and is essential for life. The bond type is nonpolar because it's bonded to itself, and so this is an example of a nonpolar bond. So oxygen is not a polar molecule. It is nonpolar because it shares the electrons in the bond equally with itself. All right, go ahead, stop the lecture right now if you want, and go ahead and see if you can draw the molecule N2 without any aid from me and see if you can get it correct. Okay, so let's check your structure now. So each nitrogen atom has 5 valence electrons around it. We'll single bond it. Right now, if I were to count around each nitrogen, there is 6 valence electrons, which isn't enough. So, but you do see 2 more dots off of each that are single dots. So I'm hoping that you predicted that all those electrons move in, and therefore the molecule nitrogen ends up having 1 lone pair. Doesn't matter where you put that lone pair. It could be top, bottom, or off to the side. But there would be a triple bond between the 2 nitrogen atoms for a total of 8 valence electrons off of each. Again, nitrogen has failed its octet, and it is a stable molecule. Okay, the type of bond is nonpolar, so I'd label this with NP, and this is a nonpolar bond, and it's a nonpolar triple bond, and again, the molecule is complete. All right, so far I've showed you molecules other than hydrogen where fluorine, oxygen, nitrogen, they follow the octet rule. Those atoms, when we're done with the Lewis structure, you should have 8 valence electrons around it. The homework that I'm going to shortly assign to you, almost all the molecules will follow the octet rule, so the central atom will typically end up having 8 valence electrons around it. But just like everything I've talked about in this class before, understand that not every molecule follows the octet rule. It's more of a guideline. So while most molecules do follow the octet rule, not all of them have to. Now, I've already talked about hydrogen being hypovalent, where it is less than 8 electrons. The other element that you will classically see that does not follow the octet rule, in which it is less than 8, is the element boron. So if I look at this molecule BH3, boron has to go in the middle because hydrogen never will. Boron is the only nonmetal, actually it's a metalloid, but it's the only element to the right of the staircase that is in group 13. And therefore it has 3 valence electrons. And because it only has 3 valence electrons, it can only form 3 bonds. So that's what the 3 hydrogens will do. And we will form the single bonds with the hydrogens. And right there is the Lewis structure for BH3. Now if I count, there is a total of 6 electrons around the boron. It does not follow the octet rule because it can't form a 4th bond in order to get up to the octet rule. So boron forms compounds that are hypovalent, and so in the homework you're going to see an example or 2 of this. So whenever you see boron, predict that it's probably not going to follow the octet rule. And again, that's okay because it really can't. What I don't want to see you do, and this is what I've seen some students do in the test, is they just plop 2 more dots on the boron to make it have 8 valence electrons, and then I'll ask the students where did it come from, and they're like, well, it needed to have 8, so I just added 2 more dots to make it have 8. You can't do that. So it has 3 electrons to form single bonds with, or double bonds or triple bonds even, but it only has 3 electrons to share, and therefore it can only form bonds which will lead to it having 6 total electrons. The other way a molecule can not follow the octet rule is to be hypervalent. Hypervalent means that it'll have more than 8. And this can only come from the elements that are nonmetals in periods 3, 4, or 5 in the periodic table. So specifically, it is either going to be between phosphorus, sulfur, chlorine, selenium, bromine, or iodine. And the reason why it has to be these elements is it has to be a big molecule. I assume not a big molecule, a big atom. It has to be big enough that it can account for having that many electrons. And because electrons repel each other, we need to have a large enough area to put that many electrons. All right, so in the molecule BRF5, bromine goes in the middle, and it has 7 valence electrons. Now, if you're thinking to yourself, with 7, I would predict that with it having 7, that it would only want to bond 1 more time. So if I have fluorine, which also has 7, you would predict that the molecule BRF would form. And you'd be technically correct because this molecule, bromine monofluoride, does exist in real life. It is a single bond that occurs between bromine and fluorine, and this is a molecule that does exist. But I'm asking you to draw the molecule BRF5. And this molecule also does exist as well. So where does the other 4 hydrogens go? Well, the one place it doesn't go is it's not going to continue to branch off of the F. Typically, when you have more than one other element present off of a single element, it's the single element that tends to be the central atom. And so you just need to start thinking to yourself, well, that central atom has to be the solo element, so all the other elements have to come off of it. And that's exactly what happens here. So now you just start arranging 4 more fluorines with their 7 valence electrons. And in that 7th valence electron, it'll form the single bond to the lone pairs. So I know what you're saying right now. Well, you just told me that that a lone pair is a full orbital of electrons. Why would it bond off of them? Well, it's bonding off of them because fluorine is the most electronegative element. In essence, it's the baddest bully in the street. It wants to get to its octet. And if it doesn't have its octet full, it will force other elements to bond to it so that it can achieve the octet rule for itself because it is so electronegative. And therefore, in essence, it forces bromine to bond, even splitting up its lone pairs to do so, and therefore this molecule can exist. Now, if I were to count around each fluorine atom has 8 valence electrons, which will always be the case for fluorine because it is the most electronegative. Once it fulfills its octet, it will no longer bond. But it forces bromine to bond more often, and if you count, each dashed line is 2 electrons, 2, 4, 6, 8, 10, and the one lone pair off of it left gives bromine, 12 total electrons. So it has 12 electrons around the bromine, and that ends up being the most electrons you'll ever have. So central atoms can have 8 valence electrons if they follow the octet rule, or they can have 10 or 12 valence electrons if they're hypervalent. You will never have a molecule where the central atom will have more than 12. So if you have an element that is in periods 3, 4, 5, or 6, and you end up having usually a subscript like BRF5 where the fluorine has a 5. If you have subscripts of 5 or 6, more than likely the molecule is hypervalent and will have more than 8 electrons around it. Okay? And again, you just can't identify until you just start getting enough practice with it. So now what I'd like you to do for your homework is to do the following next 3 pages. I want you just to do the bond type and the Lewis structure for the molecules on pages 2. We'll post the answers to these first 2 columns in Canvas on Wednesday so you can check your work over and see how well you did off of it. Now be careful. A couple of the molecules in here I have slipped in here are not all covalent compounds. Okay? So for example, if I were to do an example problem with you, NH3. First of all, what type bond is this going to be? Well, it's going to be nitrogen is going to bond with hydrogen. Because they're 2 different nonmetals, this is going to be an example of a polar bond. This is a polar covalent bond. The nitrogen is going to go in the middle, and nitrogen's got 5 valence electrons. There are 3 hydrogens, and so you would draw the Lewis structure where you form the 3 single bonds with the hydrogens, and now nitrogen has got 8 valence electrons around it. There is the Lewis structure for NH3. NaCl, sodium chloride, what you need to identify immediately is sodium is a metal and chlorine is a nonmetal. And therefore, when they form a bond, metals and nonmetals, as we just got done taking your test on it, do not form covalent bonds. They form ionic. So you have to be careful. I do throw a couple examples of this in here so that you don't now mistake ionic compounds and just start to connect the dots. So sodium, with its 1 valence electron, will donate its valence electron to chlorine, making it positive and chlorine negative. When you are done with an ionic compound, the particles, the atoms that are left are no longer atoms but are ions, and that's what holds it together. The attraction of the positive ion to the negative ion will cause it to form the ionic bond. Okay? Most of the compounds you're going to draw are going to be that of covalent compounds, but do identify when you look at the compound to draw that if it's a metal, that more than likely you have an ionic compound and the Lewis structure will be very, very different. 3. And one other thing, as you get to pages 2 and 3, some of these molecules that are bolded, these end up being larger molecules where there's more than one central atom. These atoms tend to form bonds and they tend to be bigger and bigger molecules where they tend to just form different types of bonds. And so with that, you're going to have more than one central atom. So not just one atom where everything else comes off of it. So these that are bolded, I've given you a hint that the molecules are going to spread off and form more than one central atom. So when you're done, or if you struggle with these, reach out to me, or my answer key will be provided on Wednesday and you can take a look at these. But give it a try and see if you can do these problems without any help. And if not, later, like I said, I'll supply the answer. You can check it over and you can see where you might have went wrong. Again, this is an honors class, so I want to challenge some of you guys with being able to do harder structures where they're not always just fairly easy, basic structures where you have one central atom and some hydrogens around it. That's pretty simple. We're going to add the complexity of these, and that's the purpose of all these tables, just to give you a lot of practice. So by the time the test rolls around, you should be very proficient at these skills. All right, so thanks for listening. Again, do the first 2 columns of pages 2, 3, and 4. The next lecture on Wednesday and Thursday, we will then assign the next 3 columns on the same pages, and this is going to be looking at what geometric shapes these molecules attain in 3-dimensional space. All right, so again, thanks for listening, and if you have any questions, reach out to me as soon as possible. And 4.